Satellites. In this video we'll be talking about different types of satellites and the motion of satellites. If one body rotates around another larger body, the smaller body is called the satellite if gravity is the force that's acting on them. So examples include planets around the Sun, our Moon around the Earth, but then also man-made satellites around the Earth as well. In fact, each body rotates around the center of mass of the two-body system. However, because one of the bodies is significantly larger, the center of mass is effectively at that larger body. So let's consider a circular orbit, with r being the radius of the orbit and rb is the radius of the larger body, so the radius of the Earth, for example. Because the satellite is moving in a circular path, it must experience that centripetal acceleration due to gravity, and it's directed towards the center of the path. So we know this from previous slides, with the acceleration given as the velocity squared divided by its radius of motion. Linking this with Newton's second law, we find that the force of this gravity is given by mv squared on r. This one is not on the formula sheet, but you'll be required to derive it really quickly in the exam. So it's just a matter of multiplying this equation by m. So now if we equate the centrally directed force due to uniform circular motion, and we equate it to the gravitational force, we get this equation here. And if we simplify it for velocity, for example, we result in this equation. So looking at this equation, the speed of the satellite depends only on how far away it is from that central body and the mass of the central body. The period depends on the distance away and the mass of the central body, which means that the mass of the satellite has no effect on the speed or the period. We just had a look at the derivation for the velocity of a satellite based on the mass of the central body and the distance the satellite is away. So if we square that equation, we get it here, and we rearrange the equation of the velocity of an object based on its distance and its period, which is this one here. We have to square this just so we can equate the two v squared parts of the equation. Simplifying and rearranging, we can find that the period of a satellite is only dependent on how far away it is from that central body and the mass of the central body. So this leads us into some relationships between the Sun and the other planets in the solar system. So the Sun is about 99.8% of all the mass in our solar system. So in any two-body system, with the Sun being one of the bodies, the center of mass of that system is going to be at that Sun. And what that means is that using the previous equation, we can determine the velocity of any planet that's orbiting the Sun based on the distance that it is from the Sun. And the further the distance is, the slower the body orbits. Mercury, for example, orbits very fast compared to Neptune. This isn't really part of the course, but I thought it was really interesting. This is an artist's depiction of the satellites that are man-made that orbit the Earth. You can see they orbit in different paths, and you can kind of make out some of the paths even though the dots are individual satellites. So we have a lot of satellites in this orbit here, as well as a few other different orbits. You can visit the link provided on the page to see what satellites are out there, what they do, who they belong to. But United States obviously has the most satellites, and actually private companies like SpaceX are planning to put a lot of satellites in the future, and the private companies will probably have more at that stage. You can also see the satellites that are man-made that are put out there are used for various purposes. So a lot is communication, Earth observation like weather, and a few for GPS as well. Now for a satellite to orbit the Earth, it has to orbit around the center of the Earth, being the center of mass. You can see on the left-hand side, the three orbits in this diagram are around the center of mass of the Earth, whereas on this right-hand side, these orbits are not possible as the center of the orbit does not coincide with the center of mass of the Earth. So there are different types of orbits that the satellites can take, and one is a geostationary orbit. And what that means is that geo and stationary, the satellite is above the same point on the Earth at all times, so it can monitor that particular location. This means that it must rotate in the same direction as the Earth, and it must be an equatorial orbit, so it's lining up with the center of mass of the Earth. What this means is that there's limited spots that satellites can take. We don't want them to crash into each other. There's certain spots that are allocated for satellites, and you might have a certain distance that your satellite has to be within, and if it encroaches to the next zone, that could be risking collision with the next satellite. So your satellite has to be rotating in that particular zone. Geostationary satellites are good for surveillance, being military, weather, and good for communications because the line of sight is not broken. The disadvantages of geostationary satellites is because they have to have that orbit that times with the rotation of the Earth, the satellite has to be really far away. So that means the signal strength has to be high, there's big time delay, and the detail of the images that it produces is very limited. If a satellite was to be launched to be in a geostationary orbit, its speed must be high to maintain the timing of this orbit. Now, Earth rotates on an axis of 24 hours, and the point on the surface of the Earth has a speed of 465 meters a second. So there's a significant speed increase from the surface of the Earth to the point being in orbit. So it's advantageous to actually launch the satellite in a west to east direction to take advantage of this 465 meter initial speed boost to get to the required velocity that's needed in the end. Another type of satellite orbit is polar orbits. These overcome the disadvantages of geostationary satellites. They orbit north to south, and they're a lot closer to the surface of the Earth than the geostationary satellites. These satellites orbit the Earth about 14 times a day, which takes about an hour 40 minutes for one lap. And what happens is for each lap, they observe a different strip of the Earth, which is west of its previous orbit because of the rotation of the Earth. So you can see on this diagram, the satellite orbits this strip, the Earth will rotate slightly, and on its next lap, it will be imaging something slightly west of what it previously imaged. And then these images can be stitched together and the information taken from them. Now, the orbits aren't truly polar, being perfectly 90 degrees, but they're around about aligned at 98 degrees. This means they're retrograde orbits, meaning they're opposite to the rotation of the Earth. And the advantage of this is the satellite looks at the same part of the Earth each time, every day. So the question for this video, name 2 advantages and 2 disadvantages of geostationary satellites.